In this video, we're going to introduce Darcy's law, which is the fundamental law for all groundwater flow. We just finished a little unit on hydraulic head, and in the text, he goes to porous media, where he then introduces Darcy's law. And then the next chapter, he goes to the flow equations, more into Darcy's law. We're going to reverse that a little bit. We'll introduce Darcy's law and then mention porosity in this video, and then we'll have a next video we'll go through some of the other properties of porous media. So the notes to fill out start here in the notes, and I'm actually going to drop in a video I recorded on this from the LID class. If you've taken that class, you've noticed already that there's a lot of overlap between the first few days of this groundwater class and the short groundwater unit in that class. So I'll drop that video in here, and then I'll come back later and insert something and add a little bit more to that. We're going to talk about Darcy's law. Darcy's law is the fundamental law for groundwater flow. Everything in groundwater is built off of it. And it was developed by Henry Darcy, who is the city engineer for the city of Dijon, France. He's also the same Darcy of the Darcy-Weisbach equation for pipe flow. So Darcy set up this experiment that looked kind of like this. So we had water flowing through a porous medium, sand, dirt, rock. I think he had different kinds of sand. And then he set it up so he had a head at one end. So H in, or maybe I'll put a 1 in there, and then H out, I'll put a 2 there. And he found that the flow through there was proportional to the change in head, the delta H. So up here you see delta H equals H2 minus H1, and proportional to the area of the cross section. So the cross-sectional area there. And he also found that different materials, different porous media, had different properties. Some would go fast and some would go slow. And it's also proportional to the length. So his equation, pretty straightforward. It says that the flow is equal to, and I'm going to go skip some space here. I'm going to put some more stuff in there a second. H2 minus H1 over L. That's the hydraulic gradient. So the little bracket thing, that's the hydraulic gradient. And it's proportional to the area. And different materials had different properties. Some went fast, some went slow. So we came up with K, which is, there's still some space there, the hydraulic conductivity. So that's a property of the medium of the material, hydraulic conductivity. Now, H2 minus H1, H2 is lower than H1. So notice that that's going to be negative, right? So we want a positive flow going this way. Water flows downhill, so the flow is going that way. And so we want to have positive flow. We need to put in a negative there. So when we develop equations on this, if you end up with your water going uphill, you probably forgot that minus in there somewhere along the way. K has properties. It looks like it, so this is dimensionless. It looks kind of like a velocity. It's not really velocity, but so it might have units of like feet per day or meters per day, centimeters per second. The number I have in my head for a landfill liner is 10 to the minus 7 centimeters per second. It has to be below that. We can also pull this A over on the left-hand side, and we can have Q over A, and that's called, we might call that, it looks like a velocity because it's going to be units of feet per day or something, but I'm going to call it a specific discharge. We'll get in a second why that's not a velocity discharge. Sometimes called the Darcy velocity, because again, it's not an actual velocity. So the equation for that, if I pull the A over to the left-hand side, and we can use, some people use a little q for that, which I like. Some people use a little v for that, which is a little confusing because it looks like a velocity. So the units we get for that, we have q equals, and keeping our negative in there, k, and then we just have the gradient in there, hydraulic gradient, and I'll write it this time as delta H, delta L, or it could be X or whatever. Some people also call the hydraulic gradient, they use an I for that. So they'll say Q equals KIA here, or Q equals minus K, little q minus KI. As I keep mentioning, that's like a velocity, but if you look at the cross section of a dirt down here, the soil, the sand, the water is not going through these particles. So most of the cross-sectional area is actually filled up with solids. So if you remember from your fluids, a velocity is a flow divided by the cross-sectional area we go through. So we're going to define a Vx as actual velocity the water is going. Now it's going to be wiggling through, it's going to be wiggling through there, right? But the average velocity going through there is going to be the flow divided by the area, that's a Q, sorry, area of the water that's actually going through there, right? So like a pipe. Well, the area of the water, or the area of the void space, is the porosity times the total area. Porosity is the volume of voids, or the open space between the particles, divided by the total volume. So I'm going to use an N for porosity. Again, for whatever reason, different people use different terminology. So I'm using an epsilon or an eta or a phi. I'm going to use an N for the porosity, which is one of the common ways we do it. The groundwater class, I put a note here that the text actually uses, I think it's a psi for the porosity, and an E for the void ratios. The porosity, again, is the volume of voids over the volume of the total box. The void ratio is the volume of the voids over the volume of solids. That's not used too much in civil engineering, I don't think. And matter of fact, I might say mistakenly sometime in the class, I might have the porosity synonymous with the void ratio, but rigorously speaking, it's the volume of voids over the volume of solids. But the porosity is always the volume of voids over the total volume. I think in civil engineering, and N is used more commonly. The author is a geologist, and maybe in his applications they use a psi most often. So if you look in the text, there'll be a psi in there. So if I do that, that equals Q over N times A, or remember, Q over A is our little q, our specific discharge, so it would be equal to Q over N. Or we can write it that the seepage velocity, that's the average linear velocity. Maybe write that out, average linear velocity. It's how fast the water is actually being transported. That's going to be equal to, again, keeping my negative there, K times the hydraulic gradient. I did H2 minus H1, and then I said delta H over delta L. How about this time I go farther and I do a D over DL. That's the hydraulic gradient there. And then divided by N, the porosity. So let's do an example of this in a second. So here we have two wells, monitoring well 1, monitoring well 2. We have 900 feet between them. They're about the same depth there. Looks like the water table slopes down with the ground surface from 1 to 2. Groundwater often goes generally in the slope of the land, but not always. So we want to know how long it takes to get through there. So I'm drawing these wells here. I'm going to show you just for a second here what a well looks like. So this is, I copied this into your notes. This shows a couple monitoring wells. So these are, I worked in underground storage tank cleanup for consulting firm for a while. And so these are like the monitoring wells we would put in at gas stations. First, this one here, they call it an water table observation well and piezometer. Piezometer means pressure meter. So they're just trying to find out, they're put in to know where the water is. So you have the screen in it, you drill the hole, and then you put a pipe in that's smaller than the hole, and you have a screen on there. So the water's actually coming in the screen. It's filled around there with the filter pack, gravel, and then you want to seal it off so stuff doesn't come down from the surface, and then some bentonite clay or something, and then you fill in the annular space and you seal it off. An interesting note on this one, it shows here on the second one that the piezometer is down, so it's letting water in here. So the level in the well, it's all sealed off everywhere else, tells us the head down here. Now it shows the water table here and the head there lower than that. So water goes downhill. So what this tells me is there's actually a vertical component to the flow. So the water is kind of going down this way. So it's lower head down where the screen is than it is up here. That's assuming it's a water table, an unconfined aquifer, that there's no layer between here. It's not a confined aquifer. So I mentioned several times Darcy's law is 3D. And one of the sites we worked on, we had this. It took us a while to figure out why this one deeper well was lower in head than the others around it, and I realized, oh yeah, because there's a downward flow going down there. All right, so let me go back up to our example here. That third page, that fourth page, I guess it is our next video. All right, so I have the monitoring well 1 and monitoring well 2, and I have information on the well. I have information, by the way, it's 900 feet in between. Hydraulic conductivity has already been measured or estimated at 18 feet per day, and the porosity is 0.24. So what I'm measuring is I have the TOC is top of casing, so it's the elevation up here, and then DTW is depth of water. So it's the distance from the top of casing down to the water level. So you drop a tape in there, you can get one that actually has a little thing at the end. It'll beep when it hits the water. You read it off at the top of the well. All right, so we want to know the groundwater travel time from monitoring well 1 to monitoring well 2 in days. So first thing we need, again, our Darcy's law says that Q over A, we also call that a little q, equals minus K times the change in head times the change in length. I don't really have an area between these, right? I mean, what do I use for an area? Yeah, but I can take the area out of the equation, just find the velocity there. And we know that, I'll put a comma here, the velocity the water is actually moving, Vx, equals that quantity over n, or equals, I can write it here, minus K over n, where n is the porosity, times the change in head times the length. So I need the gradient there. So I go up here, the depth of water, and I might I'll put in here, I kind of wrote over that, but the water table elevation. The elevation of the water table, this first one, 1052.6 minus 12.5 would be 1040.1. And monitoring well 2, the actual, this is the water table elevation, the actual elevation of the water table. That's what we want to know, the total potential, the total head. 1045.3 minus 14.2 would be 1031.1. So the delta H would be 9 feet. So our gradient, our change in head over length, equals 9.0 feet over 900 feet equals 0.01. We can put units on feet per feet. Remember, it's negative. So I say, what's the groundwater gradient? It's 0.01. It's actually negative 0.01 in the direction of flow. So I can plug that into my equation. So Vx equals minus K, which is given at 18 feet per day. I need the porosity in the denominator there, 0.24. And this equation here times our hydraulic gradient of negative 0.01. So you see the negatives cancel out. So that equals minus 0. No, not minus, plus, because they cancel out, right? 0.75 feet per day. So then the time it takes to go 900 feet equals 900 feet it has to go divided by 0.75 feet per day equals 1,200 days. It's a long time. For groundwater, groundwater is slow in general, but it varies a whole lot. And you see these hydraulic conductivities vary a whole lot. All right, so that's an introduction to Darcy's law. This is the basic equation. Q equals K times A times the hydraulic gradient. The specific discharge, which I'll call little q, equals K times delta H to delta L. And again, for both of these, there's a negative in front because the gradient is negative in the direction of flow. How fast the water is actually going and how fast something is moving with the groundwater would go is the Vx, we might call the seepage velocity or transport velocity or average pour water velocity. That's this Q, the specific discharge, divided by the porosity. So it's faster than that. So it's K times the gradient over N, and again, I put my negative in there. And so we did an example there where we came up with the total, the gradient is the gradient of the total head there. So we came up with the total head, found the gradient, and then found the time it takes. All right, so our next video, we're going to move on into aquifer storage properties, and then you'll have a couple of homework assignments on that. All right. Jumping back in here, I put something at the end of the notes here. We had in our groundwater travel, we are assuming a single gradient through there from beginning to end. That's not really true, especially with a unconfined aquifer. If we look at it, it actually looks something like that. And that's based on the fact that as the water table goes down, the height gets smaller. So our area gets smaller. And we're going to do, in a couple videos from now, we'll do equilibrium well equations, and that actually matters. So there are some simplifications, the Dupuy-Forchheimer equation or Dupuy assumptions. There's actually a square in there. And also, it could be changing because of boundary conditions or some other things. So it's not really a straight line. In a lot of cases, it's a straight line. One gradient is a pretty good assumption. But just put it in the back of your head that it might not be uniform. And if you can get more wells in there to define it a little better, the more the better. Also, Darcy's law is three-dimensional. So these are a couple figures from the text here pasted in here. So water flows downhill. So if the head in B is higher than the head in C, you know it's going from B to C, assuming it's all connected. So you know the water is going this way in general. But if I look from B to A, they're screened in different parts. So the well at B tells me the head at this depth. The well at A tells me the head at this depth. And it's all connected. Again, there's layers. They might be kind of slightly different aquifers, but if it's all connected, the fact that A is lower than B means that you're flowing from the B to the A. So you have an upward component of flow, right? High head down here, lower head up here, and it could be the opposite. So Darcy's law is actually three-dimensional, so it's not just flowing in one direction. We actually had an underground storage tank site where we had exactly this, and it really confused us until we were like, oh yeah, that's right. There must be some vertical component to the flow. And I could write this, if this is Q, that way I can have a Q in the X direction and a Q in the Y direction as the vector components of that. And I guess Q, actually made up and down, we usually say is a Z. And I could have a QY going into the paper. And like I said, the next page will start a new video on aquifer properties.